Good morning, all of you. So, in the previous lecture, we discussed the E2 mechanism. And in the E2 mechanism, we have discussed that if the substrate molecule contains only one type of beta hydrogen atom, we will get only one product. But if it contains two types of beta hydrogen atoms, we get two elimination products. And so, in this, the more substituted alkene is obtained as a major product. So, we say that the reaction follows Sedgwick's rule. So, highly substituted alkene or more substituted alkene is obtained as a major product because the more the number of alkyl substituents, more stable is the alkene. So, why we get Sedgwick's product as a major product, that we want to study, or we want to justify that why you get the more substituted alkene as a major product. So, the two factors that we have discussed in the last lecture, that is the stability of alkene and the low energy of activation. Stability of alkene and the low energy of activation. So, in general, if we see the general order of stability of alkenes, it's studied in the 12th standard and again in FY that the highly substituted alkene, that is, if the more number of substituents are attached to the carbon doubly bonded carbon atom. So here this is your tetra substituted alkene, which is more stable than the tri substituted alkene, which is more stable than di substituted alkene, R2C double bond CH2, that is 1 di substituted, which is more stable than RCH double bond CHR. This is 1 di substituted, which is more stable than the monosubstituted alkene, and which is more stable than the ethylene. So this is the general order of stability. So highly substituted alkene or the more substituted alkene is stable, or the stability goes on decreasing as the number of alkyl groups goes on increasing. So it is measured, the stability is measured in terms of heat liberated heat liberated during hydrogenation during hydrogenation of the alkene. Hydrogenation of alkene means here when we are saying that how we can measure the stability of the alkene. So when you carry out the hydrogenation of the compound containing carbon-carbon double bond, that is alkene, lower the heat of hydrogenation, lower the heat of hydrogenation, more stable is the alkene. More lower the heat of hydrogenation, stable is the alkene. So the alkene obtains stability. Here we can say why it attains the stability. So here these alkenes are of two types. If it is a, when we say that it's major or minor product, alkenes are of cis or trans depending upon the nature or the attachment of the groups. So it is considered that the trans is slightly more stable than the cis isomer. The trans isomer is more stable than the cis isomer. So here the example we will just see that if the hydrogenation of the molecule, that is 4 methyl, sorry 3 methyl, 3 methyl 1 butene, 3 methyl one butene. If you carry out the hydrogenation of this molecule, this is mono-substituted alkene because here only one alkyl group is attached. And so this is mono-substituted alkene. What is the type of alkene? It is mono-substituted. And so the amount of heat liberated while hydrogenation is 30.3 kilocalories per mole. Then the another isomer of this molecule, that is CH2 double bond C, CH3, CH2, CH3. Here there is only one substituent. This whole group acts as one substituent. Here this CH2 and this is the double bond. This carbon atom is attached to two alkyl groups. So it's termed as your di-substituted alkene. And this di-substituted alkene on hydrogenation liberates 28.5 kilocalories of energy. Means this is more stable as compared to the monosubstituted alkene. And if you see here the third example, that is CH3, here CH3 double bond CH, CH3. Here this is tri-substituted alkene and the heat of hydrogenation liberated is 26.7 kilocalories per mole. And so this indicates as the amount of heat liberated is less. So why this happens? Because as the number of alkyl substituent goes on increasing, the inductive effect inductive effect increases and inductive effect increases and the stability also increases. And the second thing, as the number of alkyl substituent increases, the hyperconjugative structures also increases. The number of hyperconjugative structures also increases, and this indicates the stability of the alkene. And so the point that we are discussing, that is the stability of alkenes, so it goes on increasing as the number of alkyl substituents goes on increasing. Then the next, that is the low heat of lower energy, it needs low energy of activation. So if you just study the reaction and see the energy profile diagram, that how the energy of activation required in the transition state when the alkyl substituents are more, it decreases. So here if we see the energy profile diagram of the molecule, here this is the reaction coordinate and the potential energy graph is plotted, and it is studied that if the molecule like your 2-bromobutane, here if it is allowed to react with the base, with in presence of a base, the energy goes on increasing, and here you are going to get two products. Here suppose this is alpha, this is beta, and this is beta dash. So when the beta hydrogen is eliminated, it is going to give you 1 butene as a major product. And when 1 butene is obtained as a major product, the intermediate which is going to be obtained means the proton will be abstracted from this side, and the energy needed for the activation is higher, and if the beta dash hydrogen atom, so this is the energy of activation for 1 butene, it is higher in nature. But when the 2 butene is going to be obtained as a major product, the energy of activation decreases and the stability of the, so here you are going to get the energy of activation, that is delta E, or energy of activation for 2 butene, it's less. Now, why it's less? Because the alkyl substituents which are present when the beta hydrogen is eliminated, only one alkyl group is there, that is CH2, CH3. This will donate the electron pair, means the positive inductive effect is less. But when the 2 butene is to be obtained as a product, the two alkyl substituents donates the electron pair, and the energy of activation for this is less. And so Here the product obtained in this stage, it is CH2 double bond CH, CH2 CH3. Here there is only one alkyl group, and here you are getting the formation of the disubstituted product, that is the 2-butene, which is the most stable product obtained. And so the energy of activation needed for the formation of a more disubstituted alkene is less. So this is the most important factor, that is the needs more substituted alkane needs less energy of activation, less energy of activation. Then this is not the only way, where when we say that the according to the Sedgwick's rule, most stable alkene, or the what was our concept, that highly substituted or more stable, more substituted alkene is obtained as a major product. So now the statement can be changed that the more stable, more stable alkene is obtained as a major product. More stable alkene is obtained as a major product. And so this is the most important thing that we are supposed to keep in our mind. The stability of alkene can also be determined by the resonance stabilization. Means here the inductive effect is playing the important role, and the second thing, that is the resonance stabilization, can also occur in some of the molecules. Resonance stabilization, how the resonance stabilization can take place. Suppose here the example of 2-chloro-phenyl, 2-chloro-1-phenyl propane, 2-chloro-1-phenyl propane. This is 2-chloro-1-phenyl propane. So this is the derivative of the propane. So this is the carbon alpha, this is the beta carbon, this is the beta dash carbon. Means here you will, if you treat this with alcoholic KOH, you will get the formation of two products. Here you will get the formation of the two products, that is CH double bond CH, CH3 plus, here it is CH2 CH double bond CH2. So this is monosubstituted. This is monosubstituted. This is disubstituted. This is disubstituted. And this is obtained as a major product. This is obtained as a minor product. So here it's 95% and here it is 5%. And so in this way, what is the difference? Here if you see that this molecule is a non-conjugated system, double bond, single bond, single bond, double bond. But here if you see that this double bond, single bond, double bond, means these double bonds are in conjugation. And as the presence of these two double bonds are in conjugation in the disubstituted molecule, why it is obtained? Because it is stabilized by resonance. It is stabilized by resonance. So here this can donate the electron pair here. This stabilization is obtained due to the resonating structures. CH minus, here CH3, here it is positive charge, and in this way the resonance stabilization can go on increasing and you will get more number of resonating structure. This indicates that the resonance effect also contributes in the stabilization of the product which is more substituted. And so in this way, the how we here we are able to justify, according to the Sedgwick's rule, the more substituted alkene or the more stable alkene is obtained as a major product according to the Sedgwick's rule. So this is the Sedgwick's justification for the Sedgwick's rule. Now the next point that we want to consider, that is the Hofmanns elimination. Means we are getting not only the one product, but where we are getting the two products. One is major and one is minor. When we say that the highly substituted alkene is obtained as a major product by E2 reaction. But in some cases, the less substituted alkene may also be obtained as a major product, and such elimination, less substituted alkene, less substituted alkene is obtained as a major product, less substituted alkene as a major product is obtained by Hofmann's elimination. So, one thing that we want to consider that the more substituted alkene is obtained as a major product according to Sedgwick's rule, and less substituted alkene is obtained as a major product according to the Hofmann's rule. So, whether the reaction will proceed by Sedgwick's rule or it will proceed by Hofmann's rule, it depends on the two factors. The one is the nature of living group, and the second thing, that is the nature of base used. Nature of base used. So, considering these two things, we have said in the last year also that what is the effect of this living group and the nature of the base. So, the first effect, that is the effect of living group. Here it states that as the size of the living group goes on increasing, as the size of the living group goes on increasing, the Hofmann's product goes on increasing. So we can just compare that when a simple reaction, that is RCHH, here CH2H, here this is beta, this is beta dash alpha, and here in presence of a base you will get two products, that is RCH double bond CH, CH3, then you will get RCH2 CH double bond CH2. So this is the Sedgwick's product, Sedgwick's product, and this is Hofmann's product. Hofmann's product means it's the less substituted alkene. So according to the Hofmann's rule, you are going to get the less substituted alkene as a major product, and according to Sedgwick's rule, you are going to get the highly substituted or mole substituted alkene as a major product. But depending upon the nature of this X, that is the living group, here the living group plays an important role. So that if the type of living group, and depending on that, the percent Sedgwick's product and the percent Hofmann's product is going to differ. So here suppose we will see bromine. Bromine is the first living group. The size of the bromine is smaller, and so here you will get the major Sedgwick's product and the minor Hofmann's product. But if you change the living group from bromine to OTS, that is the tosylate, the percentage of Sedgwick's product will decrease to 60% and Hofmann's product increases to 40%. And the third living type of living group, that is the dimethyl sulfonium ion. Here you are going to get 25% Sedgwick's product and 75% Hofmann's product. Means as the size of this living group increases, the Hofmann's product increases. And the fourth, that is the quaternary salt of amine, that is the trimethyl amine, is acting as a living group. Here you get a quaternary salt when it is attached to a substrate. So here you are going to get 5% Sedgwick's product and 95% Hofmann's product. So as the size of living group increases, size of living group increases, living group increases, Hofmann's product increases. And In the same way, the same effect is seen in the base also. So we'll see it in the next lecture. Thank you very much.